We have already seen that we can get the equation of motion of a system, of a D'Alembertian system from D'Alembert's principle for ideal constraints, and we also got Lagrange's equation from this principle. Now, if you have equation of motion of a system, that gives you a path along which the particle moves. For example, we consider a projectile which has Lagrangian given by kinetic energy minus potential energy as half m x dot square plus y dot square minus mgy. So, this describes a particle which is moving in xy plane, and y direction being the vertical and x is the horizontal direction. For that, we can use Lagrange's equation to come up with the equations of motion, that acceleration along x 0 and acceleration along y is given by minus g. If we solve this equation of motion with suitable initial condition, we obtain that x as a function of t is linearly dependent on t, y is a parabola with respect to y versus t curve is a parabola, and also if we plot y versus x, that too is a parabola. Now, this last curve is what we call the trajectory, the locus. This is what we see physically. So, that means we throw a particle along the slope, with that initial velocity, the particle follows a parabolic path. We got this parabolic path by solving this equation and adding the initial condition. So, the prescription is simple. If we have Lagrangian, from there you get the equation of motion, you solve the equation of motion, add the initial condition, and that will give you a trajectory or path. Consider an even simpler problem, just the 1D version of the problem, where there is no x, a particle is only going up and coming down. So, Lagrangian is simple, half m y dot square minus mgy. So, it is exclusively a function of y and y dot. Now, we have already seen that if you solve this problem, the equation of motion, and apply the initial conditions, you get the true path, which is a parabola. It is shown here using the thick yellow line. And we are also considering tiny variations of the true path. So, tiny variation in the sense we are only interested in these variation which starts at T1 and ends at T2. So, that means if we are just looking at the particle at T1 and T2, we will not know whether the particle was following the true path or it was following some other path. These are the other path, these wiggling lines. Why we are considering that? For the simple reason, we are interested in finding out that if we make a change in the path, whether from there we can get some idea about this equation of motion. Of course, we will respect the end points. So, particle must start from a particular y at T1 and must end at another time T2 at a particularly given y. That must happen. So, the question essentially is, if the particle starts at T1 from a particular point and ends up at T2 at another point, what path should it take? Are there different possibility, or is there only one path that it has to adopt? So, we ask this question. In fact, to designate the path, we can also do this, that we can plot y and y dot. We can plot the velocity versus the position. So, y dot versus y. Why we do that? Simply because that we have already seen the Lagrangian to be a function of y and y dot. So, this is why at least we would like to see how y and y dot depend on each other. I mean, we know the true path after all. The path is given by a parabola. It starts with some positive velocity and then it goes up. At the highest point, the velocity is 0, and then as it goes down, as it comes down, the velocity also decreases, the velocity is negative. So, this is a 0 velocity line. And this line, I mean this line with the arrow gives you the true path, and the other possibilities are shown here. As you can see, for example, if you are at this point, here the velocity is 0, but the potential energy is less than what it is supposed to be, and here too the potential energy is higher than what it is supposed to be. Assuming the potential energy is the total energy at the highest point, there is no velocity there, it is the 0 line. So, we see the conservation of energy alone gives us certain idea about the correct path. The path can't be this one, it is too high, because after all the energy must be conserved. So, here let us suppose we did not have any potential energy, we are measuring the distance from the ground, and ground has, let us say, 0 potential energy. Then all energy was kinetic, and intermediate values we have some mixture of kinetic and potential, and here it is all potential. Obviously, the other paths are slightly problematic simply because it will not give us the right value of potential energy. So, we can see, I mean even though we do not know, let us suppose we do not know the equation of motion, but consideration of energy alone can tell us a little bit about which path the particle should take. For example, here we can say at least the paths, the path which passes through this point are a bit unlikely, and so is the case here. However, the paths which are very close to, infinitesimally close to the true path, for them the energy conservation is not violated. So, based on this more or less, the Hamilton's principle was proposed. Define an integral L and integrate L Lagrangian with time from t1 to t2, and if you look at how j is changing as you change the path, then j is stationary for the true path or actual path or the correct path. What I mean by stationary is, let us look at the stationary value of a function. You are already familiar with the extremum of a function. A function, if it has a maximum or a minimum, the first derivative vanishes at the highest point or at the lowest point or at a saddle point as well. At extremum, the first derivative vanishes. Now, first derivative vanishes means that about this point infinitesimal changes in x will leave the function unchanged. We are looking at something similar here. The j is our function, but it is a function of path, it is not a function of time, because after all time integrated. So, tiny variation of the path will leave j unchanged. Let us look at a pictorial depiction. We have already seen our true path is basically a parabola. So, we are plotting y dot and y. This is, let us say, xy plane, and then this z is essentially here we are plotting the Lagrangian as a function of y and y dot. So, for every point on this plane we have some value of y and y dot. For that value we can get a value of Lagrangian. Okay. So, along the path for every point let us calculate the Lagrangian. So, for this particular point we have certain value of y and y dot, we calculate Lagrangian, and all such values I show it here along the green, and the other side is using a brick red color. So, essentially this is the Lagrangian calculated for every point y and y dot. See, if we sum this area under this curve, what we get is j. So, if you call it a wall built along this path, then area of the wall is j. This is what we are calculating. And what about the variations? What happens when we make a variation in the path? Well, look at the figure below. Here we have a tiny change. Now the wall is built on a path which is very close to the actual path, but this is not exactly same, slightly different, infinitesimal, let's say. So for such infinitesimal variation, you calculate L again, make the wall and calculate the area of the wall. Then it says that if you are infinitesimally close to the true path, then the change in the area of the wall should be 0. So that is basically our Hamilton's principle, in the sense that if you are on the true path and you have calculated the area of this wall, which we call j, and then you make a tiny change in the path and calculate the area again, you will find the areas not changing. I mean, of course, the variation will have to be infinitesimal. And I would like to show you this Hamilton's principle that, very simply geometrically speaking, that area does not change. That leads us to equation of motion. And how so? Let us consider again the old picture, that y as a function of t. So the motion starts at time t1 and it follows the yellow line, which is essentially our correct path. And consider this a break rate line, which is a variation. It is infinitesimal, and the deviation between the two, I mean the true path and the the variation, that I depict using green. So basically that yellow plus green gives us the break rate. Now what we do is we just give them some name, y, t, and we add a parameter alpha. If that parameter value is 0, then we have the true path. If the parameter value is non-zero, then what we are doing is we call this green function to be y, to be eta, and then we multiply a parameter alpha with this variation to add to the true path to get our final path. So this y function of t and alpha is basically the break rate path, and we multiplied a parameter alpha with the green one. So the correct equation should be yellow plus alpha times green gives you the break rate, which is the functional form here. Yt alpha is equal to yt 0 plus alpha times eta t. So you see this eta is basically the variation in the path. It could be infinitesimal, and alpha is just a single parameter. It's a scalar, and we can set it 0 to get our actual path, and if we leave it to be non-zero but small, then we get infinitesimal variation. Okay. Now j as a function of alpha, meaning we are now following this variation, so this break rate path, then j as a function of alpha is L. We replace y by yt alpha and y dot by y dot t alpha, and then we integrate over time. Now if j has to be stationary with respect to variations, after all we can get the variation by using alpha. Remember, when we set alpha to be 0, then we get back true path. So first order changes in the sense that tiny changes, just like the extremum discussion we had before. That tells us that if we take a derivative with respect to alpha of j and evaluate the derivative at alpha equal to 0, then it should be vanishingly small. That is the idea of having j stationary close to alpha equal to 0. That is supposed to give us the true path. I mean that should give us true path. Now we calculate the change with respect to alpha of j. So del j del alpha Of course, we can push the derivative in because the integration is over time and alpha remains unchanged. So, we can simply push it in and use the chain rule to get del L del y del alpha, and add to that del L del y dot del alpha. Now, this last term, remember, y is basically a function of time, it is a coordinate, it does not have any intermediate variable. So, as such, the total derivative and partial derivative are same as far as so that means total derivative with respect to time of y and the partial derivative are identical. So, we can write, I mean, like in this case, the del 2 y del alpha del t, and then we can interchange the order of differentiation del 2 y del t del alpha. So, this is essentially a total derivative of time with respect to time of del y del alpha. So, we just manipulated the last term a bit, and then look, this second term, that integral gives us del L del y dot and ddt of some term del y del alpha. What we do is the old trick that we did at the time of getting Lagrange's equation, it is the same trick here. We write the total time derivative of both the quantity del L del y dot and del y del alpha minus ddt of del L del y dot and del y del alpha. Once we got it in this form, the first term is easy to evaluate. It is basically the total time derivative and integrated with respect to time. So, we just have to evaluate it at the end point, and it vanishes. It vanishes because this function del y del alpha, remember, by definition it is basically eta t, and this eta t is our variation in the path, and we mentioned that we have to choose the path in such a way that the variations at the end point are vanishing, T1 and at T1 and T2 is 0. It goes back to that old discussion where we mentioned that what if the particle started at T1, took some path to come back exactly at time T2 to the position where we are looking for it, then which are the possible path it could have taken. This is why when we are trying to address this problem, we choose eta t such that it does not have any variation at the end point. So, our path always starts and ends at the right point, correct path at correct time. Now, if these 2 points, I mean eta t1 and eta t2, if they are 0, then the of course first term is 0. So, we have only the second term, and also we have the first integral in the first line. If we collect these two and arrange a bit, we can already see it looks like our Lagrange's equation. But anyway, what we have actually del L del y minus ddt of del L del y dot, the whole thing multiplied to del y del alpha and then integrated over time. Now, this form, the terms within the curly bracket, we can call it, let us say, m, and by definition del y del alpha is eta. So, this integration is nothing but like m times eta integrated over time, but the eta is arbitrary. If eta is arbitrary and this integration has to vanish, in that case m must vanish for all values of time. Okay. This is called fundamental lemma of calculus, which is proven in many books on calculus. It is one of the elementary lemma. Now, if that happens, that means m is 0 for all time, and that gives us a condition on L that ddt of del L del y dot minus del L del y must be equal to 0, but this is nothing but Lagrange's equation. I mean, when we get it this way, this is also called Euler-Lagrange equation. So, both the terms are used interchangeably. Now, this equation, Lagrange's equation or Euler-Lagrange equation, it follows from the search of true path, or rather to be more correct, it follows from Hamilton's principle, which simply says that when you integrate Lagrangian from the starting point, start time to end time, and you demand that variation of that integral must vanish if the variations are about the true path, then that automatically leads to Lagrange's equation. So, which is quite good. That means that now we have two options. We see that this using this equation of motion is completely analogous to Hamilton's principle, or using that integral form. Often it happens for physical problems, the integration is easy or very useful. We shall look at certain examples, of course, but before that, the one word regarding the generalization. Until now we were working with a 1D version of the problem. The Lagrangian was simply function of y and y dot. But then what about generalized coordinate? I mean, what about if Lagrangian is function of many generalized coordinates? Okay. Now generalized coordinates are independent of each other. I mean, that is how we choose them. As such, for each of the independent coordinate, each of the generalized coordinate, we can create a variation leaving others unchanged, or we can do simultaneous variation of all generalized coordinate, but each one can have its own eta. So for ith generalized coordinate we can have eta I, and then if you look at our equation here exactly, instead of a simple term we will only have a summation here, and we will have eta I, and there we will have del L del Q I minus ddt of del L del Q I dot. Now eta i's are independent, and that means that individually the coefficient of this eta I, this in that case MIT, that must vanish, and that will give us Euler-Lagrange equation for each generalized coordinate. The extension is straightforward. So it's particularly useful now. I mean, we have another powerful principle, variational principle. It does not have to be applied only to a dynamical problem. This particular result, it can have other usage. We will see some examples, and also we will extend this Lagrange's equation to Lagrange equation of first kind. We have already seen that, but this time we will get the Lagrange equation of the first kind in a more usable form. Hamilton's principle is quite general and can be extended to systems with constraint. Let us suppose we have written the Lagrangian with coordinates qi which are not generalized coordinate. What we mean is we have chosen coordinates which still have some constraint relation. So this constraint relation must also be satisfied along with the requirement of the true path. Now requirement of the true path or the correct path, we mentioned that the first order variation of the time integral of Lagrangian, that L dt, that quantity, should give us a stationary value about the true path. That must also hold true for each constraint. As such, the prescription is we add all such constraint relation after multiplying by a multiplier to our original requirement, so that they are all satisfied simultaneously. Now, instead of doing the mathematics with L, now we need to do it with L plus lambda m times Gm. Gm's are the constraint relation as we have seen before, and there is a sum over m. If we carry out the steps exactly the way we have done before, we end up here where we have the first part looks like Euler-Lagrange equation, but we also have something coming from the constraint, and particularly we see the derivatives have now appeared, del Gm del Qi. Now delta Qi's are not independent, so we cannot say their coefficients trivially vanish, but we can certainly choose k coefficient, I mean k number of delta m, such that k of the equations are valid. So that means for such delta, for k equations we will have these coefficients 0 by our choice of lambda m's. For the remaining one, we can choose the variation of delta qi independently, because now the number of coordinates, number of independent variable reduces to n minus k, which is exactly equal to the degrees of freedom. So, once we have reduced the coefficients to that number, it is possible to take linear combination of delta qi's to find a new set of delta qi which are independent of each other, which essentially means that basically taking combinations of this equation from this coefficient. Basically, our argument is same as before. There too we stated that we make this coefficient vanish for k constraints by choosing, for k equations, k number of coefficient, by choosing the lambda m carefully, and the remaining ones we can do it by choosing appropriate linear combinations. Okay. And this is particularly useful, this relation. Why so? Because in many cases, if you compare it with the traditional form of the Euler-Lagrange, Lagrange's equation of the first kind, where we wrote like for ith point particle, mass times acceleration, and from there subtracted the external force must be equal to lambda m del g m del r I. Now, this form is slightly advantageous in the sense that this above form that we got now, it can be easily extended to extended objects. Extended objects in the sense where you have the motion of the center of mass, and also you may have rotation about the center of mass. For such extended objects, we know exactly how to write the Lagrangian easily. On the other hand, writing down Lagrange's equation of the first kind for the extended object might be cumbersome, because not everything can be defined using point particles. Particularly, we refer to here the ladder and the dumbbell equivalent. If we had this equation, it would have been easy to use the above form.